Wonderful. Thank you, everyone, for bearing with us. We're very happy to have Akhil, who is just across the courtyard at the KICP. And with no further ado, take it away. Yes.
All right. Thank you, Seth. So I gave a presentation that is pretty much 95% similar to this a few weeks ago at the Journal Club at the other building. So if you already saw that, I won't be offended if you just leave now, because I don't think this is worth like hearing about again.
You turn the sound off on your computer.
Okay, it's going to be
The sound on your computer.
Yeah. All right, so the talk is, I just changed the title a little bit, to kind of emphasize that I'll be talking about Journal Limit Theorem. So the talk is basically going to be about what is eternal inflation, how the picture of eternal inflation is ruined by rare fluctuations or what I call large deviations. And I'll kind of work my way up to that, starting from this claim here. So I'm sure all of you have at some point of time seen this potential. So this is kind of like a drawing model for how an inflaton behaves during inflation. So what I have here is a massless scalar field that is rolling along a potential, and as long as the field remains on that flat part of the potential, the universe is in an inflationary phase. Now, the claim that I'm making is that I can describe the dynamics of the inflaton field by approximating it as a random walk. So this is a kind of semi-classical description. And I'll explain systematically why where such a description comes from. Just to kind of refresh your memory about random walks, I'll just kind of remind you. I'll kind of bring up this example of a typical random walk, which is Brownian motion. So on the left-hand side here, you have some kind of big particle embedded in a path of many smaller particles. And the problem that I want to solve is to try and describe the motion of the big particle alone without having to deal with the dynamics of all of the smaller particles. And cast in this way, the problem already has the trappings of an effective field theory, because we have separation of scales. And in the effective description, we want to kind of integrate out all of these, large number of degrees of freedom that are moving fast to describe just the trajectory of the big yellow particle. So how do we do that mathematically? So there are two ways of doing that. First is to use what's called the Langevin equation. So this is basically just going to describe the velocity of the particle, and it will have two pieces, one which will be a deterministic piece, and then there will be some kind of stochastic component to it overlaid on top of the deterministic piece. An equivalent way of describing the same thing is to use what's called the Fokker-Planck equation. So this time what I do is, instead of describing the exact position of the particle, I just kind of give it a probabilistic description. So I define a object called pxt, which is some kind of probability distribution, which captures essentially the same information as the Langevin equation. And on the right-hand side here, I have some kind of animation which shows how this works for the simple case where the deterministic part of the velocity is just some constant. So the red part is basically a solution of the Langevin equation, and the blue curve there is the probability distribution that corresponds to the solution. All right. A slightly more interesting example is what's called the Ornstein-Uhlenbeck process, because unlike the previous case, this actually has an equilibrium solution. So if you wait a sufficiently long time, the system actually asymptotes to Gaussian distribution, and the way it works is like this. So the deterministic piece is basically harmonic potential. So the system has to kind of be confined to this region eventually. All right. So what does all of this have to do with de Sitter space? So let's take, just to kind of establish some convention, I'm going to work with fixed de Sitter space, and I'm going to do field theory in a fixed de Sitter metric. And what that means is that my Hubble rate h is constant, and I can visualize de Sitter space-time by this cartoon here, where I show two distinct slices at two separate instants of time. So I've kind of just visualized all of space as this planar sheet. And I've also indicated the Hubble rate by drawing these circles, the size of which is proportional to H inverse, or they have the same diameter as H inverse. And the size of these circles remain constant because H is not changing. All right. Now, to get some intuition for what's about to happen, let me kind of take a small detour and talk about dimensions of objects in de Sitter space. So let's say I were to draw some kind of arbitrary shape on my plane. So this is basically the spatial component. Since space is expanding, I also expect that the line will expand. And I would like to define the dimensions of this arbitrary shape in some way. And let's say I use the following method to define dimensions. So what I do is I count the number of H inverse sized balls that I need to cover the shape that I've drawn on my surface. So the number of balls are going to keep increasing as space expands, but the scaling with H should remain constant. All right. So for instance, suppose this arbitrary curve was a simple straight line. The length of that line would be something like AX, and I can just cover it with circles aligned end to end. And therefore, the number of balls that I need to cover this line is just AX over H inverse. And specifically, the exponent of H from this relation is 1. And therefore, I find that by this definition, the dimension of a line is 1, which makes sense because a line is a one-dimensional object after all, right? Now, suppose this line has a mathematical property that as it expands, it gets more structure. So on the left corner there, I have a line, and then I'm kind of tracking it as it expands with time. And if it reveals more structure, then I can ask the question, what happens to its dimensions as I defined before due to the structure? So I once again repeat the same exercise from before. I just cover the line with these H inverse size balls. But now I realize that because of its structure, I need to actually use more balls to cover this line with more structure. And I can actually incorporate the additional number counting of these balls by just modifying the exponent of the relation from the last slide. And that small modification, gamma there, it should be kind of suggestive, is what's called the anomalous dimension of this shape. All right, so if gamma is a very small number, I can always Taylor expand it, and I will get a log. And suppose I did this whole problem in Fourier space, I would get basically a log k over ah. And because there is a log of a, and a is just an exponential in time, this log is linearly proportional to time. All right. So the lesson here is that these kind of logarithmic corrections are a sign of structure that appear in de Sitter space. And these lines are some kind of stand-in for long wavelength modes of a quantum field. And for such a field, the structure is basically just generated by quantum fluctuation. So there's nothing really magical about it. All right. Now we can actually do some field theory in de Sitter space. So let's take a scalar field, put it in a de Sitter background. I can look at the equations of motion. And I'll assume that the scalar field is massless, so I lose the last term there on the left-hand side. I will also be only interested in the long wavelength modes, so I can take k over ah to be much smaller than 1, so I lose that term. And under the assumptions of slow roll, the double derivative of the field with respect to time is very small compared to the phi dot piece. And if I use all these assumptions, I find that I get a deterministic piece for the time evolution, and this should be compared to the deterministic piece from the Langevin equation. All right. Now I can embed this information into a correlator. So if you were to give me a correlation function that involves a phi cubed operator, then taking the time derivative of that will give you basically 3 phi squared phi dot, and I can replace that phi dot with the phi dot I computed there. All right, so this blue piece here corresponds to the blue piece from our Langevin equation from before. And now comes the quantum piece. So for the quantum piece, I have to do a loop calculation because loops are what generate those log k over ahs. So first I noticed that if I just look at the power spectrum of a massless scalar, I get this famous scale invariant power spectrum, which is 1 over k cubed. But if I also were to compute the 2-point function of a phi cubed operator with the fundamental scalar, I also get something that's proportional to 1 over k cubed. But this time it appears with a loop correction multiplied, right? And inside, if I compute this loop, I get this log k over ah factor, which is what I earlier said is the signature of quantumness. And therefore, if I were to take the time derivative of the phi cubed phi correlator, I would find that it actually contributes to the power spectrum. Right. So this is an instance of operator mixing. All right. So now I have two pieces. I have the classical piece, which just came from looking at the equations of motion. And now I have the quantum piece, which came from a loop calculation. And if I now combine both of these contributions together, I have something that begins to look like the Langevin equation, right? Except that it's in terms of these correlators. And if I fill in these coefficients correctly, I get what's in the green box below. All right, but there's no reason that we should restrict ourselves to just the phi cubed operator. I can just generalize to any phi n operator. So this is any composite operator made of a fundamental scalar. And again, if I calculate all of the coefficients carefully, I get the following Langevin equation for how these correlators should behave, right? And on the bottom half of the slide, what I've really indicated is that, again, I'm stressing the fact that the first term is the classical term and the second term is just from the quantum bits, which have now been incorporated as some kind of white noise into the dynamics. All right. So how about higher order corrections? So we have a classical piece and a quantum piece separately. To get the next higher order correction, we have to kind of combine these two things. And to find exactly what that contribution is, we just play the same game that we did before. So all I have to do is I have to take a phi to the power n operator and somehow make it behave like a phi to the power n minus 2 operator, right? And I have to use the interaction vertex. And the way I do that is by drawing a diagram like this. So this time I just use my lambda phi for vertex. So this is just one particular example. And then I get a phi to the power n minus 2 kind of thing with a linear in time factor multiplying it. But this time it's order lambda. So we'll see how this gets incorporated into the Fokker-Planck equation eventually. But first I have to actually tell you how to get a Fokker-Planck equation from the expression in this page, right? All right. So we need a couple more ingredients to get a Fokker-Planck equation from the Langevin equation for the correlators. So the first ingredient is what's called ultra locality. And by that, what I mean is, if I'm only concerned with the dynamics of the long wavelength modes, I can use the fact that A, space is homogeneous and isotropic, and B, the different Hubble patches basically are not talking to each other. So if you have a mode that kind of spans across different Hubble patches, then you can consider the dynamics in each of those Hubble patches independently. And what that means is you can just replace the field with something that is independent of position for these long wavelength modes. And once I do that, it allows for the possibility to describe the evolution of phi, or the time evolution of phi, by a probability distribution p phi t, right? And specifically, I can imagine that all of the correlators that I want to calculate with my phi operator are just some kind of ensemble average calculated over these probability distributions, right? And therefore, I can take my original Langevin equation. I can replace all of those expectation values as some average over the probability, and do some basic manipulations like integration by parts to arrive at the Fokker-Planck equation. And this actually resembles the Fokker-Planck equation that I introduced at the beginning for Brownian motion. All right. So how about the higher order corrections? So I mentioned that the higher order corrections come from mixing the quantum and classical pieces together. And it produces, for example, a diagram like this if you have a lambda phi for theory. And it produces a correction to the Fokker-Planck equation, which has this form. Okay, so going back to my claim that I made earlier, that we can just approximate the dynamics of a field in the flat part of the potential as a random walk. I think this sufficiently justifies the claim that I made. Right. Now, I should also mention that there's this valley that the field will roll down. And if the field actually gets to that point, then that Hubble patch actually reheats and converts into standard model matter. And the inflationary phase ends, at least for that Hubble patch. All right. Now, to get a better visual representation of what p phi t actually means, I can use what's called the bacteria model of thinking about the inflationary phase. So I go back to the picture I introduced before, where I had these discrete spatial slices at different instances of time. And this time, instead of drawing circles of size h inverse, I'll draw small squares of size h inverse. And I will represent the value of the field in each of those Hubble patches. This is the ultralocal field by some shade of green. Now, because there is this noise and drift at work, what happens is that in each time step, first, because this is de Sitter, a single Hubble patch will divide into a multitude of Hubble patches, exactly like bacteria would, right? And two, the color of green, the shade of green or the value of phi in each of those Hubble patches actually gets jostled around a little bit as each of the children, quote unquote, inherit the value of the parent bacteria, right? All right. So if I were to kind of take this and somehow try to animate it, I would have initially some bacteria. It would multiply, and at each instance when it multiplies, it inherits the values of its parents, and then also suffers some slight mutations because of the quantum noise. All right, so the thing I really want to highlight here is this fractal structure that I was talking about earlier. So the effect of quantum noise here is that when you go from, for example, this step to this step here, the regions of light and dark kind of roughly remain the same. It's just that the quantum noise adds a little bit more structure to the picture. in exactly the same way that it added structure to the line that we discussed earlier. All right. Now, if I were to construct some kind of histogram of all of these field values, and if I were to kind of normalize it appropriately, I could then interpret that histogram as a probability density function of the field values, and that really is what P phi t means. And the dynamics of how P phi t evolves over time is what the Fokker-Planck equation is telling. All right, so let's kind of take a look at how the probability distribution evolves. So first I have just one patch and then 4 patches, so the histogram is just getting built up. But also notice on the left-hand side that there is a subtle movement of the probability distribution to the right, and this is because of the classical drift of the average value. I'll just let it play out. Okay, so the probability distribution is kind of becoming slightly wider and also moving slightly to the right as time goes on. However, this cannot happen indefinitely because you know that there is some kind of reheating surface or some kind of valley at some point along this phi axis. And if these patches hit that value of phi, then the universe or the corresponding patches reheat. Right. So let's see what that looks like in 2 scenarios. So the first scenario is when the quantum noise is actually kind of weak, which means that the distribution is rather sharp. And the second case is where the quantum noise is strong or comparable to the size of the drift itself. So in the first case, if the quantum noise is weak, the distribution remains rather sharply peaked, and over time, all of these patches kind of cross the reheating surface and they just get converted to standard model matter, or and Big Bang cosmology kicks in. In the second case, if I have some more variation due to a larger quantum noise, you see that not all of the patches actually end up getting reheated. Some population of it still remains behind, right? And therefore, we have this scenario where some population of the green patches that I showed you earlier actually never reheat. And that scenario is called eternal inflation. So this is when some regions of space never really gets converted to standard model matter. So how do I?
Sorry, just to understand, you have a so for your Fokker-Planck equation, you have this higher order correction.
Right.
Is that what you call quantum noise, or is
No.
that's
okay.
not right? So,
No. So the quantum noise term is the first piece.
Yeah.
And if you observe, that is actually independent of the potential. So that does not contain, for example, lambda.
Mhm.
Right. So this piece will always be present.
Okay.
So this will always be present. And then in the second piece.
that should be there even for free fields here.
Right.
Right. So the second piece is so there is a piece proportional to your
Yes.
your lambda.
Yes, there is a second piece proportional to it.
That's what you added, right?
Right,
So
right.
what's the effect of that piece?
Great. So the effect of this, I don't want to, okay, maybe I can go back to the.
I mean, also for weak noise versus strong noise.
Right.
For you're just saying that it's just the H is big or not. And
Yes, it actually depends on the ratio of the strength of the this piece to the strength of the drift piece.
yeah. But roughly speaking, I understand the weak,
Yes.
strong, but the size is controlled just by H.
Right.
Right. So so what's the effect of
The effect of the third piece is actually it controls the decay to the equilibrium distribution. So for instance, let me just quickly go back to this picture here. So if you notice this curve, I told you that it kind of asymptotes to an equilibrium distribution, right? So the equilibrium distribution is a Gaussian centered at x equals 0. But you notice that there is some kind of decay constant associated with how fast it arrives at that equilibrium.
Well, there's a piece where it's how fast the center drifted to that point. That's just some classical rolling. But
Right.
then you think that the speed, how fast the whole distribution become Gaussian around the center is controlled by the third term. Is that the
Yes. So if I were to modify the third term, let's say modify its coefficient, it would change the shape here.
yeah? But that sounds like, I mean, of course it will change the shape of potential. It will change the speed of classical rolling as well.
Yes,
But that's not the third term, right? The third term is or it is
that is the effect of the third term. It actually affects the rate at which you approach the equilibrium.
Okay, but mostly, I mean, this shape itself is determined by the classical.
Yes, but the equilibrium shape itself, and we did this calculation explicitly in an earlier paper, the equilibrium distribution itself is unaffected by that small term. But in the eternally inflating scenario, so that is something like the scalar field theory with 5-4 potential. Okay, so I was here.
So again, whether you stay in eternal inflation or not, it's mostly a statement of age in comparison with the classical rolling.
Yes, in comparison with the classical orders, yes. So, any other questions? Okay. All right. So, how do I now quantify this? How do I detect whether eternal inflation actually happens by looking at the probability distribution of P pi t, which is the object governed by the Fokker-Planck equation? So first, I noticed that the rate of decrease of the total area under P phi t is basically the proportion of patches that get read.
Can I stop you? So in what sense are the classical equations of motion satisfied?
What do you mean by that?
Well, ordinarily, I would say that in field theory, the classical equation of motion is satisfied with some kind of expectation value of the quantum distribution.
Right.
And it seems like in this eternally inflating scenario, there's some piece of the probability distribution which is not following the classical evolution.
Right.
So how do I understand that?
When it reaches the bottom, I think if you eternal inflation must be in a regime where quantum fluctuation dominates over classical rolling. I see. But otherwise, you will eventually hit the reheating surface.
So when things like that happen in quantum field theory, usually what we do is to say, oh, I've got the wrong effective Lagrangian. Right, because there's some piece of quantum fluctuations which is renormalizing the classical evolution. Like it's like you're saying there's some kind of
I think there you are not really relying on the mean of the field, right? It's just there's some very big fluctuation. I don't know what the equation of motion probably doesn't really play a role whether when you exactly in the eternal inflation regime, right? So equation of motion, whether you trust it or not, yeah, it's probably true that you shouldn't trust there are big quantum fluctuation normalizing your effective Lagrangian.
Okay, so this is kind of the resolution to what I'm about to discuss. So let me come back to this. So the equations of motion are relevant, but okay, let me come back to this. So all right. So I can use the uppercase P phi t to construct an object called the probability of reheating at time t. So this is the probability for any given patch to reheat at a particular instant of time. And clearly you can see that the longer it takes for a patch to reheat, the larger its volume is. And therefore, if I were to compute the expectation value of the volume of all of the patches, then I can use that to check whether eternal inflation has happened. Because if the expectation value of the volume of the patches go up, become infinity, then that signals that eternal inflation has happened. So I just plug in this object PRT. I multiply the scale factor times some kind of initial volume L cubed. And within the integrand, I see this competition between rapid expansion, which tends to make the volume bigger, and this reheating probability, which tries to make the volume smaller. And the rapid expansion actually wins out if the variance of the probability distribution is larger than some number, which is to say that the quantum noise, if the quantum noise is sufficiently large, you have eternal inflation, which is exactly what we saw in the cartoon from the last slide. All right. Now, this is just again another cartoon of what happens post-inflation or post-reheating. So suppose we were in that yellow spot, which corresponds to one particular cell. Then after reheating, our horizon would expand. And it seems to be the case that if you believe eternal inflation is happening, that we are in some kind of family of, we seem to be embedded in some kind of family of patches, which have all kind of collectively reheated. Because if our horizon were to touch any of these black surfaces or black patches, which are still in the inflationary phase, then that would be a significant distortion to our space time that we observe. All right. Now let's try and do a concrete calculation with a specific model. So this is something we picked out of the EFT of inflation. And I'll just point out a couple of things for this model. The this is in terms of the scalar metric fluctuation zeta. And zeta is related to the phi field that we have been discussing so far by the simple transformation in the limit of the slow roll parameter going to 0. And what that means is if I were to draw those animations again from before in terms of zeta, I will find that the reheating surface is actually moving now rather than the field drifting towards zeta. Also, because of some non-linearly realized symmetries of the zeta field, there is no polynomial interaction in terms of, or there is no.
So this is the EFT of inflation,
yes,
but taking some particular choice of various couplings.
Of various what?
Couplings in the EFT of inflation.
What do you mean particular choice? Like whatever was in the EFT of inflation.
Well, EFT inflation has many free parameters.
Oh, okay. Yeah. Yeah, we will see that. We don't make any assumptions about what the parameters are. This is kind of the general expression we get from just using the fact that there is some kind of diffeomorphism invariance for the fields.
And why are you in the eternal inflation?
We'll calculate the condition for eternal inflation, and then the parameters will come in.
This distribution must depend on the parameter.
Right.
So
it does. So what I was going to say was that the condition from before, which is that the variance should be greater than 1/6, actually gets converted to a condition on the parameter delta zeta, which is the amplitude of the power spectrum. Okay. So yeah, that's what, if that's what you were asking, yes, this is why we took a particular model.
That translates into some parameter choice.
Yes, exactly.
Yeah.
Right. All right. So what about the non-Gaussian correction, which we know how to calculate now? So that's the quantum plus classical bit that we were discussing earlier. So the next higher order correction is going to have the form of that cubic derivative term there. And if I do some kind of back of the envelope calculation to determine the size of each of these terms, then I find that if the Gaussian piece is assumed to be order 1, then the non-Gaussian piece is much smaller than 1. In fact, it scales as h squared over lambda squared, where lambda is the cutoff of the EFT of inflation, and h is the input parameter. And therefore, naively, one would expect that since the non-Gaussian term in the equation is small, the corrections to the conditions we derive from the Gaussian case should also be proportionally small. But it turns out that that is not the case. So what happens is, if you compute the condition for eternal inflation, you get the first thing, which you see on the left-hand side there. But if you compute it with the non-Gaussian corrections, you get a condition which looks like this, which importantly involves this ratio f pi squared over lambda squared. The problem is that f pi squared over lambda squared is much greater than h squared over lambda squared, which was the size of the non-Gaussian term from the Fokker-Planck equation. And this seems to be some kind of contradiction.
F pi is, again, F pi is phi dot.
F pi squared is phi dot, yeah.
And okay. And lambda is just some generic.
Yeah, it is the, yeah, it can be. So I just, in the interest of space, I just fixed it here. It can be here or here. Yeah. Right. So what's really going on? Why is this contradiction happening? And it's basically related to the question you were asking earlier about the equation of motion. So just to kind of pull my way up to the resolution, let me just take a very simple toy example. So I just take a Gaussian random walker. So this is a walker which samples a Gaussian probability distribution to determine the size of each step. So on the left-hand side, I have what's called my microscopic theory, right? And then on the right-hand side, I downsample the same trajectory. And I ask the question, what is the probability distribution that this walker had to sample to get this downsample trajectory? And it turns out that, you know, if you add a bunch of independent Gaussian distributed random variables, the sum is also distributed as a Gaussian. And that's really what's happening here. Now, I can do the same exercise for a fixed step length walker. So this is a walker which can either move by +1 or -1, but nothing in between. I take the same trajectory, downsample it, and you can clearly see that the downsample trajectory kind of roughly looks the same as the one from the Gaussian walker. And in fact, this is manifest if you repeat the same exercise and you ask what the probability distribution is of the sum of the downsample walker. And in fact, this is just a manifestation of what's called the central limit theorem. So I'm going to call the output of the central limit theorem my EFT. And as with any EFT, it has a cutoff. So this is only valid so long as my x, uppercase X, is much smaller than √n. All right. Now, again, this is just another way of trying to demonstrate the same thing. Both of these trajectories are constructed by sampling either the Gaussian random walker or the fixed step length walker. But at this zoom level, you can kind of see that it's difficult to tell which one is which. But if you zoom in, you can see that the red one is clearly the fixed step length walker because it moves in these lines with well-defined slope, and the second one is the Gaussian random walker because the step size can be anything. So what's really the problem here? The problem here is that you cannot use the EFT to ask questions about the tails of the distribution. And to demonstrate this, what I do is I look at an observable which is an exponential of the X variable from before. Now, if I were to believe that X were distributed as a Gaussian everywhere, then I could use the fact that its variance is just n. And therefore, if I naively just substituted an order root n number in place of X, I would just conclude that the expectation value of the exponent of X is e to the power theta times an order root n number. However, since this is a Gaussian, I can actually compute it explicitly. And what I find is that it's actually the expectation value is an exponential of some factor which is proportional to n, right? And the reason for this discrepancy is that even though things in the events in the tail are extremely unlikely, when an exponential samples them, it acquires a very large value. And therefore, those contributions to the mean are actually proportionally large. And what that means is, even though there are these really rare events due to the fluctuations, the expectation value of observables like this blow up due to differences in the tail. So the exponential is very sensitive to the tail of the distribution. Now, if I were to carefully draw the distribution for both the fixed step length and the Gaussian Walker, I will also find that they disagree at the tail. So if I were to use that observable from the last slide and evaluate it for both the fixed step length Walker and the Gaussian Walker, I would get different results. Although in an EFT sense, they kind of look the same, which is kind of demonstrated by the fact that if I'm kind of here, roughly here, both the Gaussian and fixed step length Walker have roughly the same distribution. Whereas if I go far away towards the tail, they have different behavior at the tail, which is exactly what the exponential is sensitive to, right? Now, just to come back to your question about the equations of motion. So what this is really telling us is that.
Sorry, what are IF and IG?
Those are, so this was taken from the papers. Those are what are called rate functions. So what I'm really doing there is, can I write on the blackboard?
There's an eraser over there.
Yeah. So what I'm really writing there is e to the power, or what I'm plotting there is e to the power minus IF or IG, where IF is just x squared over 2. Sorry, IG is x squared over 2, and IF is the actual corresponding object for the fixed step length distribution. So yeah, I can show you the actual expressions from the paper, but yeah, this is just something I just pulled from the paper directly. I should probably have removed those legends.
Okay.
Yeah, but the main point here is that the tails are different for the two microscopic distributions, and the tails actually remember information about the microscopic physics, which the EFT actually does not contain. And therefore, if you were to compute the expectation value of an observable which looks like this, then it becomes sensitive to the microscopic physics via the tail. And so that is kind of, if you kind of put all of these insights together, that is what you kind of conclude, which is that first, an observable which involves an exponential is sensitive to the tail. And that's exactly the kind of expectation we were trying to compute to determine if eternal inflation happened or not. And therefore, and finally, the tail is sensitive to the microphysics of the problem. And therefore, what we really conclude by putting all this together is that eternal inflation is really sensitive to microphysics. That is not quite captured by the EFT of inflation.
But this is more like a problem with EFT of inflation, that particular.
Right.
So if I just have a simple scalar theory,
right. If you believe that that is the full theory of everything, yes.
Square.
Right.
It's a little dumb, but it is nevertheless a theory.
Right.
And I would expect effective, eternal inflation happens
Right.
in the regime for that theory, which is quantum fluctuation is much bigger than the effect of whatever the interaction is. Right, because and that in that, if you just look at that Lagrangian,
Yes.
the kinetic term should be more important than whatever the interaction is.
Right.
If anything, that makes that Lagrangian more valid. Then
Right. Well,
make the naive part of the Lagrangian more valid than having to including additional corrections. Right. So in the sense that it's the kinetic term that's dominant, right?
Right. It is, but
I mean, this is something like with the oddity of this EFT of inflation. Somehow you have to be having this picture of a phi dot is some classical thing,
right.
And you expand it around, right?
Well, okay, maybe this relates to the question you were asking earlier about the equation of motion. So I showed you this Fokker-Planck equation, or let's focus on the leading Fokker-Planck equation for the Gaussian case, right? So I can write a path integral description of that property distribution. So which roughly looks like E theta, e to the power, let's say, the variance of the noise times integral of theta or the square. All right. Now, one way to, or a different way to kind of cast the same conclusions is to note that the equations of motion from this path integral is basically d squared theta over dt squared equals 0, right? Which has the general solution theta t is just some constant times t. Now, all I'm saying is that the EFT is designed to be valid around this particular solution, where alpha equals 0. Whereas eternal inflation is sensitive to the other solution, which is when alpha is an order 1 number. So order 1 times. Because those are the trajectories. So if I were to draw zeta, those are the trajectories which are actually kind of which look roughly like this. So the point I'm trying to make is that the EFT of inflation is an expansion around the wrong saddle. In the same way that the ground state of a canonical ensemble is different from the ground state of a Gibbs ensemble. Because once you introduce a chemical potential into the problem, you have a different, you're basically expanding around a different saddle than if you had zero chemical potential. And that should remind you of the structures that we are talking about here. So,
but isn't this consistent with this picture that when you do EFT of inflation, you do imagine there's a rolling field, right? And you're expanding around it.
Right.
That's the EFT of inflation. But when you think about eternal inflation, usually people sort of pictures like you are as close to some hilltop or some very flat piece, and
right.
So there the mean value of the field it doesn't really move, right? But you're just having larger oscillations around it, right?
So I told you that there was this kind of like change of variables that happened when I switched to switch between talking about phi to zeta, right? So the corresponding picture in terms of phi, where if you want to now imagine a field phi that is drifting,
right,
is that the second saddle or this saddle corresponds to the field just remaining constant.
Yeah.
So that's the case where the quantum diffusion is kind of exactly opposing the drift. and keeping the field at a particular place. Which, when you move to this frame, just makes zeta appear as if it is linear in time. Because phi remaining fixed means zeta is linear.
So there obviously then phi dot is small, right? So then and the EFT of inflation shouldn't work in that case, right?
But phi dot has to, yeah, okay, right.
I don't know. Maybe I'm still. I mean, normally a naive picture of inflation is just you are on some hilltop, but you're just doing this. Right there's no phi dot. So.
But are we still talking about slow roll internal inflation? Like,
well, I'm just saying, all it's very, very flat. So that you know you are dominated by very, very flat, also known as phi dot, very small.
Okay.
I still don't understand what the answer to my question is. So it's like, suppose I'm an observer,
right?
You know, sitting in the middle of all of this,
right?
Do I eventually fall down and reheat or not? Because the classical equation of motion said, I'm sitting here in my little patch of inflating universe,
right,
and I should be watching the scalar field slowly come down its potential, and eventually I fall down and reheat with it.
Right.
So do I not see that?
No. So if eternal inflation were to happen, you're more likely to not see that. For the reason that your fluctuations are always pulling you in the opposite direction. So if you did not have any fluctuations, like you said, you would eventually roll down and fall into that valley. But because the fluctuations are exactly lining up and opposing your classical drift, you're kind of remaining in place. So the reheating surface is always farther away from you.
Sort of like a regime where the volume of inflation, inflationary patch is always exponentially larger.
Yeah.
Than the patch in which the inflation has ended.
I guess maybe it would have helped if I were to draw like a volume weighted probability distribution rather than just the probability distribution.
Yeah.
Because if I drew up,
and then we end up with interesting discussion about the measures.
Yeah, yeah. So if I were to draw this object, say that and if you were to now think of this as the basically governing the dynamics of what your scalar field is doing, then you can see that for the when eternal inflation happens for the vast majority of space, you're likely to find yourself in a situation where you're on this saddle, or correspondingly on the saddle where phi is a constant. The phi scales linearly with phi just remains 0 or
But non-Gaussian entity is actually normalized by 2-point function. Right. So it's some 3-point function divided by some 2-point function, right? So it's not clear. You're just saying one of the things that are likely to be very big. Right.
one of which thing?
I thought your argument was that the EFT does not capture the likelihood of one of the zeta becomes very big. Now patient will have a very large fluctuation. Right. But I thought that this also 2-point function should also have the same information. Why should the non-Gaussian entity specifically?
Okay, so I think what we were trying to do originally was, or our expectation going into this calculation was that if we were to use the noun Gaussianity, we would get a better handle of basically the condition for eternal inflation. Right. The problem is that the corrections computed within the EFT of inflation do not tell you whether, or gives you this like contradictory answer, which is a sign that you can't do that calculation within the EFT of inflation.
In what sense are you saying that the analysis depends on the microphysics? What microphysics is it?
Oh, okay. So I guess one way of saying that is basically what I was trying to say earlier, which is that the EFT of inflation is an expansion around this saddle, and I can't get to this other saddle by a perturbative calculation. So
within EFT.
Within the EFT. So I would kind of interpret that as
why is that microphysics as opposed to some infrared secular divergence?
oh, because well, okay, in general, infrared secular divergences in so what happens in de Sitter is that the UV modes don't just remain UV modes, they just shift into the IR. So when you calculate, for example, a loop diagram and find that there is a quote unquote IR divergence or a late time divergence, it's actually not purely an IR divergence, it's something coming from the UV.
Right. But the UV is usually taken to be in some kind of Bunch-Davies vacuum, so it's featureless. So in what sense is there microphysics that you're probing?
Well, the EFT of inflation has a cutoff, right? So in some sense, there is some scale beyond which we are not allowed to go.
Or maybe this is I don't know, maybe I would say is that this is a question of a UV completion, such as a simple m² phi² theory can answer. Give you a better answer. So in that sense, this is a UV issue, like what exactly the term look like.
Right.
I mean, I would have said that it's sort of an infrared issue in that, you know, what is one doing? One's taking the quantum fluctuations in the Bunch-Davies vacuum, which is just some scale invariant, you know, UV spectrum. And then at some point, at some scale, one is saying those fluctuations have become big enough that they decohere and become classical. So you can stick them into your Fokker-Planck equation.
Right.
Okay. The scale at which that decoherence happens, it's not obvious to me that has anything to do with the cutoff. I mean, it's sort of like things become classical and decohere when they pass through the horizon.
Right.
That's where sort of where all the growth comes from. It's when things are outside the horizon. But that's a very infrared scale.
But I think the point is a bit like if you want to compute the tails of the distribution, organizing the calculation in terms of correlation functions near the peak of a Gaussian is not a particularly reliable way to do that. And in that sense, it's like a UV kind of thing.
Yeah, so I guess my question, so I mean, at some point there was a slide saying, well, it's sensitive to the tails. Why are the tails related to microphysics?
I think it's just that you need to know the microphysics to accurately calculate the tails. And then strangely enough, there's some observable that's sensitive to the tails in this particular.
Yeah.
Okay, so for I can give you like a very quick. So this was calculated, for example, for a fixed step length Walker, right? So the object X here, X tilde is just the average of steps. So for a fixed step length Walker, the maximum value of X has to be.
Right, yeah, no, this is some analog problem. I was saying in actual inflation, what's playing the role of these two? What two different microphysics would I use to see? Is it sensitive to like whether I have m squared phi squared or phi to the fourth?
I think it is.
Is that the
sensitive.
claim?
Yeah, I think it.
Well, yeah, I actually have a similar question, which is like, even if I told you the model of the world is m squared phi squared, is that actually enough information to calculate the tails, or do I really need like a literal UV complete model of quantum gravity to compute these things?
I would think that the m squared phi squared is enough.
Unless you're worried about like Planck.
Yeah, but why aren't I worried? Like the tails go
Okay,
arbitrarily
then yes,
far
then
out.
it is not.
Like I have infinite volume, I
Yeah,
can
then
win
it
against
is
any.
not. But you just moved essentially the cutoff scale from phi dot to f1.
Yeah, but that's what I'm asking. So like, if you wanted to do this calculation reliably, like
Sure.
if you need a theory of quantum gravity, like.
Sure, yeah. Strictly speaking, if you have n Planck size fluctuations, you wouldn't have to worry about those things.
Well, I wonder if. Can I then still use the same scale factor as before, like e to the power 3 HD? Because that really is the source of the problem, right? The fact that that scale factor is kind of this, has the form of this observable here in this analog.
Yeah, that's a totally separate question I have, which is whether like, at some point, ignoring back reaction becomes really bad when you have really large, like when you get far out on the tails, obviously these things do back react. And so, yeah, there's some competition between these various things.
Right. Yeah. So this is in fact something that I'm actually looking into, like the effect of back reaction and when it is, whether that kicks in before this effect kicks in.
Right.
But, yes. Right. Yeah. So thanks for the questions. I'll think about it more, but yeah.
In terms of the time,
Okay.
is there, how close were you to the end of your talk?
Oh, this is done. I'm.
Oh.
Oh. Yeah,
Let's
that was-
thank you. Yay. Great. Perfect.
Sorry.
Thanks.
Sorry.
I saw you were asking a physics question.
Yeah.
How long are you doing?
Oh, the time, yes, yes. Good, wonderful, thank you.